Hi everybody, and welcome to our series of webinars that speak about EMS as an add-in to Inventor. Today we're going to be talking about parameterization in EMS using Inventor iLogic, and Dr. Ahmed is going to be the presenter of this neat feature in EMS for Inventor. So again, I'm going to make Ahmed the presenter now. And again, welcome everybody. There we go, sir.
Thank you, Adam. Welcome again to our series of EMS seminars. And today we have for you one of the nice feature of Inventor is the iLogic. So basically, you can parameterize any model dimension using the iLogic feature. I'm not going to go over how you create how you create a dimension iLogic. Let's assume that all of you are Inventor users and you already know how to do that. I'm going to briefly refresh your memory how to create a study in EMS. So in this particular situation now, the distance, I parameterized the distance between the coil, and this is, by the way, you know, this is a speaker. So see, you have a almost dozen permanent magnets. You have also the core and the voice coil. And the principle of a speaker really is a mixture of permanent magnets and a voice coil that vibrates because of the interaction of the electromagnetic field between the between the voice coil and the permanent magnets. So in this particular case, we chose to parameterize the position of the voice coil. Of course, for simplicity, I simply parameterized or used iLogic only for one variable, but you can use it for 2, 3, 400, doesn't matter really. There is no limit, you know. As far as EMS is concerned, anytime you change your dimensions, okay, for instance, if I want to now put a dimension to probably exaggerated, maybe put it to 20, say okay, 0 and 10, okay, so it says maximum span, so get done. All right, there you go. So you can see that my voice coil now, at this position, it moved up. Okay. If I create a study now, simply is going to take the current values of all model dimensions. So if I had more variables, then it's going to take that. So I can create a study, and to refresh your memory, the EMS comes with 5 modules. The magnetostatic, again the magnetostatic or DC magnetic. If you have coils or windings that have constant current, a DC current or voltage for that matter, and or permanent magnets. Usually the designer wants to find force, torque, inductance, flux linkage, saturation, fluxes, That is what is magnetostatic is used for. When we say magnetostatic means there is no time variation. Because the electromagnetic field don't vary as a function of time, there will be no eddy currents. So there is no proximity effect, no eddy currents whatsoever. Electrostatic is a dual of magnetostatic in the sense now instead of solving for the magnetic field, now you solve for the electric field. And we know from the Maxwell's equations, if you want to solve for the electric field, the material property that's really relevant material property is really the permittivity instead of the permeability. If you want to solve for the magnetic field or magnetic flux density, it's really the permeability that comes into play. Electrostatic, electric field solver, is really the permittivity instead of the permeability that comes into play. And when you talk about permittivity, we talk about the electric breakdown or corona sparking. So if you apply a voltage difference through a very small gap filled by air or any other dielectric, at one certain point, that dielectric is not going to support that high electric field. And as a result of that, the air or the dielectric atoms, they get ionized. And once they become ionized, which lead to sparking and corona. And if you have a high voltage application, high power, high voltage electrostatic can be very useful. And it doesn't have to be high voltage. I mean, if you have a very small air gap, even a voltage which is not very high could actually produce sparking and corona. Electroconduction is again electric field solver, but now instead of considering only insulators, now we look at just conductors. So if you have a conductor system where you want to find the current density, current flow, some people call it electroconduction and some people call it current flow. So how the currents flows in a conductor system. And you apply voltage, and anytime you apply voltage across a conductor, the electrons that start flowing, and hence they will generate an electric a current density. Okay, and the current density is of course related to the electric field via the conductivity sigma. All right.
Welcome to GoToMeeting. There are 6 other callers on the call.
The permeability is the most important variable as a material property, of course, and the conductivity. So when we are dealing with electrostatic, okay, magnetostatic, really we didn't care much about the conductivity of the material. Now if you are doing an AC magnetic analysis, both the conductivity as well as the permeability play an important role. Why? Because when you say AC magnetic means that the current or voltage changes as a function of time. And due to Faraday's law, we know any time that the field changes as a function of time, they're going to give rise to what is called eddy current or induced currents. Hence, you're going to have what we call proximity effect, skin effect, that all become important because of the induced current and the surrounding conducting materials. Of course, if you don't have any conductivity, if it is an insulator, then there won't be any eddy currents induced at all. Now,
welcome to GoToMeeting. There are 6 other callers on the call.
The magnetic field does change as a function of time, but it is a periodic change, or so-called time harmonic or sinusoidal change. So follows a sinusoidal pattern, and most of the signals, in nowadays, technology and gadgets are easy. Okay, so, but in cases you could also encounter a situation where the excitation, the current, and or the voltage are actually not time harmonic, are just transient. And transient magnetic is a magnetic field solver where the conductivity and permeability are both taken into consideration, which of course handles the eddy current, or the induced current, and again you can use the transient magnetic to study proximity effect and skin effect. Except now the excitation is no longer time harmonic, but it's rather arbitrary. So any function of voltage or current can have any shape. It can be a pulse, it can be a sine curve, it can be an exponential, anything, you name it. All right, this and again, as we mentioned last time, all of these 5 modules can actually be, except electrostatic, can actually be integrated, coupled to the thermal solver, which is a fully integrated solver inside EMS. All right, so okay, say okay now. Now it's creating a new study, and again, because I used iLogic, I changed the distance while it creates electrostatic here, but that's okay. Because I changed the distance between or the vertical distance of the voice coil that's going to go up and down and vibrate, and that's going to create the noise or the sound. Now, if I mesh, it's going to take what you see is active. So the idea of using the iLogic is very simple. Just create your iLogic table for model dimension. Again, for the simplicity, we limited to one variable here, but really, again, you can have many different variables. All right. I'm not going to go again how to apply materials and all of that. That's not the subject of this talk. But let's go and let's look at this position, 0 position now, okay, which is when the voice coil is actually touching. These are the regular materials, and you have a bunch of permanent magnets, you have a nonlinear steel 1010, and the coil, and you go straight to result stable now. When I go to result stable, okay, so click result stable. These results are for that position, okay? And again, these are the what we call lumped quantity results stable, tabulated data, all of this, they mean exactly the same thing. So for that particular position, that's what I have, okay? Now if I change the position, the study is a different position. Of course, this can be, if you have a moving object and you don't care too much about the Newton effect, then you could use the iLogic to decide different position. Let's look at now at the magnetic flux density. And actually, it's a vector plot. All right, let's pull this. So this is the vector plot of the magnetic flux density. Okay. Well, if you look closely, you see that it's circulating in right direction. But again, as we said in previous presentation, sometimes it's cumbersome. It's just difficult to know what's going on. For that reasons, you may want to use some of the handy tools of the post-processing or visualization tool that EMS has. So one of them is again the section clipping, and even for the vector plot we can do a section clipping. So if I want to take this section, now clearly I can see closer. Now I can see how the flux density is actually circulating from the permanent magnet through this tail and back. Okay, and they interact with the voice coil. When they interact with the voice coil, they're going to create what's called Lorentz force, J cross B. So anytime you put the current inside a magnetic field or magnetic flux density, I use magnetic field, magnetic flux density interchangeably because really they're related by the permeability. Okay, so anytime you put a conducting material inside the permanent, inside a magnetic field, that coil or conductor is going to move due to what is called J cross B effect, or what is called Lorentz force. So because of the Lorentz force, it's going to move up and down. All right. Now this section I can actually move it. I can move my section. Okay. And I may want to do okay, so I can look at it inside out, okay, or outside in. Okay. Again, I can look at different different planes, or I can even tilt the this is my section. All righty. Now, if I look, if I want to see at the next position, I simply go ahead and move to the next study, and you know, I could show you the mesh just to see that the mesh is going to be different from one position to another. There you go. So nice mesh. Now I could look at the for this case I can show you probably the magnetic field, and now we're going to look at the fringe plot. All right. So this is the fringe plot. The fringe plot, if I want to look at the high spots or region where I have a maximum magnetic field, or any other data, magnetic flux density, applied current, force density, so on and so forth, I could use the ISO clipping. The ISO clipping, again, it allows me to actually look inside my model and see where my maximum field. All right, so it's no brainer here is because it is a magnetic field, and magnetic field like to be stronger in air. So in the air gap, you have a higher magnetic field. If I want to go in the other way around and look at the minimum, okay, I could also do that. Of course, I can add a second and a third and a fourth and different sections, different levels of magnetic field. Now, I can move on to another study and do something else. And probably this time around I could do 2D plot. So in my 2D plot, as you remember always, we have to take like 2 points, okay? And now I'm going to do my 2D plot. All right, so those of you attended previous presentations, so they're familiar with these tools. Okay, but the purpose of the presentation today is really not just the general, the global.
Welcome to GoToMeeting. There are 8 other callers on the call.
Using the iLogic. Okay. Now, the most important thing is this. So all of those plots, probably some of you have seen it before, but this is what is the most important part of it, is results, compare results. Now, how is this important? Now, I have different studies, and suppose I want to look at in this case, the force in the x direction. Okay. And let me see here, I don't want to make this guy crash, so study 9, this guy I'm going to delete here. Okay. Because I didn't run this study, I'm afraid it could cause some problems, so I might as well, so magnetostatic. And now I want to take the force, the x direction, I'm going to add parameter, and now plot parameters. Here we go. So what do I have here? On the x-axis I have the study, and on the y-axis I have the force in the x direction, Lorentz force, so to speak. So again, this handy 2D plot tool, it allows me to actually track the values, okay, and I see that the force acting on the voice coil, as I move up the coil, actually it keeps increasing to a certain, until it reaches a certain level, okay, which is study 4. I can see it corresponds to what iLogic variable, and then it starts going down. So this is a very useful information because it allows you, of course, in a voice call situation, in a speaker situation, you probably want to optimize your Lorentz force. So this is a good tool that allows you to do so. And okay, of course, if you want to look at the numerical values of the force, is simply click on listing. You'll be able to see at its position the value of the force. Okay, so this is the take-home lesson today. Is after you create different studies, different configurations, you can at the end compare your results using compare study results. In some situation, you may say, okay, well, you know what, I don't want to keep, because look, in this situation I have different permanent magnets. Do I have to do everything once I change the iLogic variable? And the answer is no, because I can simply drag and drop, okay, or copy and paste. So I can copy study 0, copy it. Now when I paste it, it's going to keep all other variables like materials, loads, mesh, everything same, except now when I paste it, it's going to take the active study, which is in this case 10 millimeter. Okay, I'm going to call it 10 millimeter. This saves me quite a bit of time. Why? Because I do not need to go over and reapply materials and reapply permanent magnetic coercivity and strength and all of that. Say if the only thing that changes is only the model dimension, so I can go ahead and change it. And the EMS, with the help with the Inventor, is going to recognize all the parts, all the faces if you apply the boundary conditions, and reapply them again. So only thing is needed at this point is remesh. So why remesh? Well, because anytime you change the model dimension, okay, you have to remesh. Okay, that's all you need to do, and then you can run this particular study, or if you have many of them, you can go back to the root of the project and run all studies. Okay, so that is basically in a nutshell how you can use this iLogic. And again, use only one variable here for to clarity and simplicity, but you can really have many different combinations of variables. Okay, and when you create the report, it should tell you, okay, now let's say, we have HTML or Microsoft Word file, so if you create this one, all right, so it says magnetostatical analysis of 9, which means of study 9, corresponds to 9 millimeter in this case. And again, it's a full-fledged regular Word file that you can edit it. Okay. All right, so that's basically the parameterization using iLogic of Inventor. Okay, if you have any questions, or I could also show you another example of a solenoid, but the essence, in essence, is exactly the same idea. If I want to have a solenoid or a motor, transformer, speaker, actuator, you name it, okay? The idea is the same. Is just use iLogic, parameterize, and then produce different studies for each position by using copy and paste or drag and drop, and run one study or run all studies before you go home in the evening. And when you come in the morning, you will be able to compare your results using the compare results feature. So you could compare again, wherever in the table you can compare it. Okay, so force, torque, resistance, flux linkage, inductance, so on and so forth. I think with that, I'd like to ask you if you have any question for me today. I'll be glad to answer it. Okay, so I think my lecture presentation is very clear, and happy it is. Again, you want to point you, as usual, to our website, webinars. Stay tuned for our webinars. Every month we post the upcoming webinars, and if you missed one, they're archived and recorded every time, so they're here in the list of the archived webinars. You can watch them, and if you have questions about a past webinar, don't hesitate to call us. Furthermore, if you have a particular topic that you want us to cover in a webinar, we'll be glad to just contact the technical support or the sales team, and suggest a topic for the webinar, we'll be glad to cover it. And I don't want to forget always to tell you that we're very proud that we have a lot of testimonials, people, users of Inventor, or EMS, or HFOX, or different CAD platform were happy with our software, who not only happy, they even wrote you know, a testimony or a video to express their satisfaction. So you know, feel free to visit that section as well. With that, I would like to thank you very much for your time, and again, see you in future EMS webinars, and I turn the mic to Adam.
Well, thank you. Thank you, Dr. Ahmed. So I'd like to thank all the attendees again. And for any questions, as Dr. Ahmed mentioned, if you have any propositions, anything like that, we can send them to support at emworks.com. If you want us to, any topics you would like us to cover, send them to that email there, or to sales at emworks.com. And please, I mean, you can always suggest a topic there, and we'll cover it. And of course, the best place to go back and visit our recorded webinars would be www.emworks.com. And if you go to the news and events section, news and events section, you'll be able to see the webinars there and download or watch the videos, and that way you don't miss anything. So it's much appreciated, everybody. You all have a great evening. For those people logging from Europe, people logging in from the US, have a good afternoon, and people logging in from Asia, have a great night. Bye-bye now.